Hello, my name is Yunjin Ko, and this is my chemistry final presentation. So, my topic is the intermolecular forces and its effect on the boiling point. This topic will introduce intermolecular forces, effect of intermolecular forces on the boiling point, application of intermolecular forces to daily life, and several real-world problems about intermolecular forces. So we'll start by investigating the definition of the topic concepts of this presentation. So, what is intermolecular force? Intermolecular forces are the immediate interaction between molecules. It is often shown as attraction between each other. It have three different types. First one is London dispersion forces. Second one is dipole-dipole. And third one is hydrogen bonding. So let's start with the London dispersion forces. London dispersion forces is a forces of attraction that exists in every molecule. It is caused by temporary instantaneous dipoles, which have the uneven spread of electrons at any given point. It is responsible for the attractive forces between nonpolar molecules, and it is the weakest intermolecular forces. The London dispersion forces increases as the mass increases. The second type of attraction is dipole-dipole attraction. It is the attraction between the polar molecules that attract each other by electrostatic forces. It is still relatively weak intermolecular forces, but it is at least stronger than London dispersion forces of attraction. The third and last type of intermolecular forces are hydrogen bonding. It occurs when a molecule contains hydrogen atom and one of the three most electronegative elements. First, fluorine. Second, oxygen. Third, nitrogen. However, it's mainly OH bond or NH bond because there's relatively less number of HF bonds. It is a very special type of dipole-dipole attraction, and it is the strongest type of intermolecular forces because the electronegative FON atoms attract the bonding pair of electrons stronger. So here is our main investigation. How does the stronger intermolecular forces affect the boiling point? We will go through this by looking at some of the data and statistics that I have investigated during my IA. So as we can see, we will investigate the effect of intermolecular forces of alcohol on its boiling point based on this data. First, as you can see, the ethanol C2H5OH and erythritol C4H6OH4, or you can just put it C4H10O4, are in the same alcohol groups. But the boiling point of ethanol, which is 78.35 Celsius, and erythritol, which is 330.55 Celsius, are significantly different between each other. So our main point is this: what causes this difference? This is because of the difference of mass of hydrocarbon chains and the number of hydrogen bonding between two alcohols. As you can see that on a data table below, the ethanol have only 2 carbon and 6 hydrogen, while erythritol have 4 carbon and 10 hydrogen. Also, when we look at the hydrogen bonds too, ethanol have only 1 hydrogen bond attached, while erythritol have 4 hydrogen bonds attached to their hydrocarbon. This increased mass from increased hydrocarbon chain of erythritol gives stronger London dispersion forces than ethanol. As I mentioned, the increased mass causes the increased London dispersion forces, remember? And also, the increased number of hydroxyl groups, OH bond, gives stronger hydrogen bond forces than ethanol. This results in stronger attraction inside the erythritol molecules, which requires more energy to break up the bonds between them, ultimately raising the boiling point of erythritol significantly higher than ethanol. So just to sum up just those investigation that we just did, it's just really simple. Stronger intermolecular forces, no matter it's the difference of London dispersion forces, dipole-dipole attraction, or hydrogen bonding, it results the higher boiling points. So we will see the applications of those intermolecular forces in daily life from in this section. So how does intermolecular forces exist in our daily life? Well, the first one is DNA. DNA, a chemical compound that stores genetic information of our body, can only exist through strong hydrogen bond forces caused by adenine, guanine, cytosine, and thymine. So it is most crucial type of use of intermolecular forces in our daily life. So on the second one is the surface tension. The surface tension, a force that maintains water's shape and resists an external force of a liquid, is determined by its intermolecular force. Stronger surface tension. For example, a water have strong hydrogen bonds, which provide strong and stable surface tension, while other liquids with weak intermolecular forces, such as ethanol, have low capability to maintain their shape. So not just the daily applications of just intermolecular forces, there's also intermolecular forces and boiling points relationship that affect our daily life. The first one of that is alcohol lamp. Alcohol lamp uses methanol CH3OH or ethanol C2H5OH because they have very low boiling point. They are flammable liquid. The lack of strong intermolecular forces of methanol and ethanol compared to other alcohols made them a good fuel for an alcohol lamp. And the second one is cooking. It might look irrelevant, but erythritol C4H10O4 is used as a sweetener. It is used for sweetness like sugar, but it is used a little bit more different way. Unlike sugar, erythritol does not easily melt or caramelize while cooking because it has very strong intermolecular forces. So basically, it doesn't melt. So coming from strong London dispersion forces from increased mass and strong hydrogen bonding, it is used as kind of a bulking agent for low carbohydrate baked goods. So let's move on to real world problem then. How can intermolecular forces can be used to solve the oil spill problem? So to talk about this, we must go through why this oil does not mix with water problem first. Oil is non-polar hydrocarbon that only have weak London dispersion forces. In contrast, water molecules have relatively strong hydrogen bonding. Therefore, the strong intermolecular forces of water molecule make them attract strongly to each other, rejecting the oil which has only have weak attraction forces. This makes oil insoluble. So our solution is we can just use chemical dispersant to emulsify the oil. Surfactants of the chemical dispersant have two chemical groups, oil compatible and water compatible. Oil compatible group have London dispersion forces like those of the oil that allow them to mix. Water compatible group contain hydrogen bonding like water, allowing them to mix together. This reduces the tension between the oil and the water, allowing oil to break up into small droplets surrounded by surfactant molecules, allowing the oil to disperse through the water. So following the work cited that I have researched, and thank you for listening to my presentation.